Batch or continuous? Which equipment is better for your operations? Today's Heat Treat Radio episode is a lunch and learn to answer your burning questions about batch IQ versus continuous pusher furnace systems. Michael Moiseau of Erie Steel is a boots-on-the-ground expert in North American heat treat, and he'll share a bit about the history of these systems before getting into the equipment and heat treat processing differences. Doug Glenn, Heat Treat Today publisher and Heat Treat Radio host, Karen Ganser, associate publisher and editor-in-chief, and myself join this Heat Treat Today Lunch and Learn. More on our sponsor, Heat Treat Veterans, later in today's show. Let's take a listen now.
Can you talk with us a little bit about the whole history of batch versus pusher?
Sure. Thank you for having me. So interestingly enough, the pusher furnace, which we might say is a more complex piece of equipment than a batch integral quench, the pusher preceded the batch. So atmosphere pushers were around prior to World War II. And so I spoke to a number of folks in the industry and said, how could that possibly be, given the level of complexity? And interestingly, pushers were available because the atmosphere was generated by a charcoal generator. So if you think back in pack carburizing, all the way back to that, we used charcoal and some accelerator. You'd put it in a closed container, you'd heat it up, and that's how we carburized things before we had atmosphere furnaces. Well, utilizing that same concept that generated an atmosphere, put it in a furnace, and pushers were the first ones to do that. So who are the folks that did that? You know, it's Holcroft, it's Surface Combustion, it's Ibsen. I mean, all the usual characters and suspects there. I've obviously left someone out, but it doesn't matter. So these things were available in single row and multiple row configurations. They were heated with gas or electricity. I have to think that the early ones were heated by gas. And typically they employed oil quenching, although atmosphere cooling could be in the works. You know, to find something of that vintage, very difficult to find that. So maybe somebody listening to this, right, will weigh in and say, well, let me help you with that. So the batch integral quench furnace, it's post-World War II. And what precipitated the development of the batch integral quench furnace is the development of the atmosphere generator. So that's Norbert Kolber. He worked for Lindbergh. And I believe it was about 1941 that he actually published a book on atmosphere generators. I can't see where he was granted a patent for this thing. Again, it might be interesting to find that thing out. But again, Lindbergh, Surface, Ibsen, Dow Furnace Company, all of these folks had things late 40s, early 50s. And they started out and they were relatively small. So they could have been a furnace that had a tray that was 12 inches by 12 inches by 8 inches tall. I mean, you'd struggle to fit 100 pounds in something like that. But the batch furnace, by far the most popular atmosphere furnace that is available. You got a variety of processing capabilities. It makes it very flexible, a wide variety of sizes. Even today, it can be heated with electricity or gas. We'll talk about that a little bit later on. And it can employ, so you could have an oil quench furnace, you could use a polymer quench, and you could have a furnace where you atmosphere cooled the load after it was processed in the primary furnace. So during this discussion, I'm going to use batch IQ, batch integral quench kind of interchangeably. So if I say batch and I forget the IQ, or I say batch integral quench, these are all the same pieces of equipment. We have numerous names for the same thing.
You're saying basically that the continuous furnace came first because they were creating the atmosphere by using basically coal, right? Burning coal.
Charcoal.
Charcoal inside the furnace. That created a carbon rich.
Yeah, actually, it was a generator. It was a generator that was pumped into the furnace.
Got it. Okay. So it was that was confusing. I was wondering how they were burning charcoal inside a furnace, but okay.
So actually, as it was explained to me, because the pusher furnace was so much larger, when you would open the doors to put a load in, or you'd open the door to extract a load in, and to quench it, because it was so much larger, the relative pressure drop of opening a door wasn't that great. So these primitive charcoal generators could accommodate that. But in a batch furnace, arguably the door is one wall of the furnace. And you couldn't create a sufficient amount of pressure in the furnace. So it had to wait until we had endothermic generators that we could establish a furnace pressure higher than atmospheric pressure to make batch furnaces. It's fascinating.
And as you said, it is probably the most popular furnace used today by many, many heat treaters, very flexible. Okay, so batch furnace, here we go.
So let's look at the CAD drawing for a batch. So the batch furnace is primarily two components. You can see the hot zone. That is the furnace proper. It's highly insulated. It has radiant tubes in it, so we can put atmosphere in the furnace. And the heating portion does not affect the atmosphere. So it's loaded through a vestibule. So the vestibule is pressurized as well. So a load can go into a vestibule. You can close the door. You open the inner door. The load goes into the furnace. We can process it. And then, as you can see in this, we'll talk about that in just a minute, you could either quench the load or you could top cool the load. So what kind of things can we do in an atmosphere furnace? So the operations that do not require quenching, that would be, we could stress relieve, we could subcritically anneal, we could supercritically anneal, so above and below 1350, 1400 Fahrenheit. And then we can normalize. So normalizing is utilized for product like forgings or castings, where they're made at a very high temperature. You've got a multiple number of structures in the component. And what you want to do is you want to, and in fact, the term, you want a normal structure. You want a uniform structure throughout the part so that it could be machined. So normalizing is typically performed at a high temperature, and it's put into this top cool atmosphere cool chamber. So in the old days, that was termed air cooling. So it was a rate equivalent if you just set it out in air. Actually, these top cool chambers are somewhat insulated. They have cooling jackets that are in the side. There's a fan in them, so you could circulate the atmosphere through it so that you get uniform cooling throughout the load.
Michael, this isn't considered high pressure gas quenching though, right? This is just
not even close.
Not even close. Okay.
Not even
right.
Close.
Yeah.
So here we have the load going into the furnace. The vestibule door closes. The furnace door opens. The furnace door closes. We perform whatever process it is that we want. We extract the load out of the furnace, and it goes up into the top cool chamber. It's atmosphere cooled. When that's completed, then we take it out. So time in the furnace could be 4 hours plus or minus. The time up in the top cool chamber would probably be an hour or two. Once the load is extracted from the furnace and is put into the top cool chamber, once you reestablish pressure in the vestibule, you can actually open the outer door, put another load in, and start processing the next load while the initial load is being cooled. So then there are processes that require quenching. So in degree of simplicity, there's neutral hardening. So neutral hardening implies that the atmosphere in the furnace is neutral with the carbon content of the steel. So a 30 carbon steel, you'd run a 30 carbon atmosphere. A 40 carbon steel, you'd run a 40 carbon atmosphere. You want the optimum is to neither enrich nor deplete the surface carbon. You don't want to change the chemistry. Typically, neutral hardened parts are subsequently oil quenched. Then there's carbonitriding. So carbonitriding, you have a high carbon atmosphere. You also introduce ammonia into the furnace. The ammonia dissociates right in the furnace. That carbon and nitrogen diffuse into the surface of the component. It's held at a sufficient temperature to attain the case depth that is desired. Then again, it's extracted into the vestibule and it's quenched. Carburizing would be another process. It's similar to carbonitriding, except there is no ammonia. It's only carbon that's diffused into the surface of the part. Typically, parts that are carburized are oil quenched. However, there are strategies and there are components where you would carburize, then you would take the part and you would top cool it. You might take it out of the furnace and you may reorient the parts. So parts that are distortion critical, they may be oriented in one direction for carburizing and then reoriented for hardening. You may carburize twice as many parts as you harden. So the hardening load would be half the size. And then furthest down the road, the low temperature process, ferritic nitrocarburizing, that typically is performed around 1,000 degrees. That is performed in batch furnaces as well. Typical process cycles for that are going to be at temperature, hour and a half, 2 hours. And that process can either be atmosphere cooled or it can be quenched. So it depends on whether you're looking for solid solution hardening or if you're just looking for the nitrided layer and you're not trying to do anything to the substrate. So any one of these processes that we just described, again, it's loaded in the vestibule. The vestibule pressure is reestablished. It's put into the furnace. At that point, we perform whatever operation it is that we wanted to of those previously described operations. And here you can see that the load is immersed in the quench. Following the quenching operation, it's withdrawn from the furnace. So total time for quenching, 10 minutes. It actually, when it's brought up out of the oil, typically you let it sit there and allow it to drip, so that precious quench oil that you've paid your money for can go back into the quench, and you're washing and removing as little quenchant as is possible. In the heat treating operation, quenching is the single most critical portion of the operation. When we're carburizing, we have a portion of an hour that we could vary, and there would not be a significant change in the case depth of the part. When we temper the parts, you have hours. You could temper it for 3 hours, you could temper it for 5 hours, and you're not going to have a material change in what's performed. The quenching operation, the latitude that you have in quenching is in seconds. When the load is extracted from the furnace, so our typical protocol is that when a load is extracted from the furnace, from the time that the furnace door opens into the vestibule to where the load bottoms out at the bottom of the quench in a batch furnace, it's 40 seconds maximum. 40 seconds maximum. Typically, it's done in 20 or 25. But 40 seconds are maximum. In a pusher, that number is 30 seconds maximum. And this is something that you track, you keep it, it's data logged. If it exceeds that, at that point, you're going to have to perform some inspection on that load that is much higher, much more intense than you would had it not taken that much longer.
Can you just very briefly explain why is it? I mean, why is it so important? I'm assuming it has something to do with Martensite start and Martensite finish and all that good stuff. But is there a layman's way of explaining why the time to quench is so important?
Sure. So essentially what you want to do is you want to have the load at a uniform temperature when it goes into the quenchant. Because if we have a significant variation in the load temperature from the top to the bottom or the front to the back, even if the quenching operation is completely uniform, we're going to have a variation in properties, variation in hardness, certainly the probability of a variation in core hardness. And for those things that are distortion critical, absolute important that the load have a similar temperature across the load, top to bottom, inside to out when it's quenched. You typically don't have a singular furnace. And I'm going to say typically you don't have a singular furnace. You have a system. So what's involved in a system? So what we're looking at here, it's a relatively simple system. So you have a loading operation. So obviously the parts need to be loaded in baskets or fixtures. In some way, the load needs to be built, and typically there's a station for that. Following it being loaded, it's put into a preheat furnace. So a preheat furnace is identical to what we would call a temper or a draw. You can thermally clean the parts by heating them up to 800 degrees. And the other thing is that those BTUs that you put into that part are 20% the cost of getting those BTUs when you're putting it in the high heat furnace. So it just makes economic sense. You're cleaning the parts and you're preheating the parts. Then you're going to put it into the furnace. So you're going to perform the furnace operation. It's either going to be top cooled or it's going to be quenched. And then you're going to take it, and if it's top cooled, you're going to stop that top cooling operation at 300 or 400 degrees. So you're going to put it in a cooling station allowed to cool to room temperature. If you quench the part, if you're modified mark quenching it, that's 250 degrees plus. If it's quenched in regular oil, it could be 150 to 180 degrees. Typically, you don't want to, the next operation is going to be to wash it. You don't want to wash hot parts. You want to allow them to cool to room temperature. Sometimes you do, but more often than not, no. So then there's the wash station. So you're washing the parts. You take them out of the washing station and you allow them to drip. Then you're going to put them into a temper. You're going to temper it for 3 to 7, 8 hours, something on that nature. You extract the load from the tempering furnace. You put it in a cooling station. You allow it to cool down to room temperature so that you could then unload it. So as you can see this, the way that is accomplished is with this transfer cart. So the transfer cart extracts the load from a loading table. It pushes it into the preheat furnace. It pulls it out of the preheat furnace. It pushes it into the batch furnace. The batch furnace quenches it. But then when the outer door, the vestibule door is opened, the transfer car has to go in and get the load, pull it back onto the transfer car. It pushes it across the aisle into the cooling station, picks it up, puts it in the wash, takes it out of the wash, puts it into the temper, takes it across the aisle. When the tempering's finished, extracts it from the temper, puts it on the cooling station. So that transfer cart is an important piece of equipment. But you can see that there's a lot of moving parts on this. So you'd say, why would you do this? Well, again, because of the flexibility of the batch furnace, in this example, batch furnace number 1 can be performing neutral hardening. Batch furnace number 2, at the same time, can be carbonitriding. The neutral hardening load finishes, and the next load that goes in there could be annealed. After the load is annealed, then you could take a load and it could be normalized. Then you could go back and you could neutral harden again. So if you don't have multiple loads of the same thing, this offers a degree of flexibility that it almost is not available in any other type of atmosphere processing equipment.
And the fact that you have more than one furnace, more than one temper furnace, more than one high heat furnace, more than one temper furnace, that gives you almost, not exactly, but it gives you closer to a continuous process, even though each furnace is a batch, if you will.
Correct. So there are charge cars that are automated. So the charge car knows where the loading station is. It goes to that loading station. You could either have a human unload it, or in the highest degree of automation, it gets there and you have a PLC that's overseeing, that's supervising this entire operation, and it would know to take that load onto the cart, where to take it next, and what to do. So it becomes a semi-automated method of heat treating.
Know a heat treat veteran? Heat Treat Today is building an archive to remember individuals who have served in the military and now work in the heat treat industry. If you know someone who has given of themselves to protect and serve others and now works in heat treat, submit their name, contact email, and any information you know to the Heat Treat Veterans submission page, www.heattreattoday.com/veterans-nomination-page. You can find the link in this episode's show notes too, or even reach out to myself at bethany@heattreattoday.com for further information. Again, if you'd like to submit their name, email, and any information you know directly to the nomination page, that's our website, www.heattreattoday.com/veterans-nomination-page. Now back to today's episode.
Let's move on to the pusher, the continuous system.
So the pusher, as you can see in this description, this is the vestibule, the furnace, and the quench. So we've just broken it down into the pusher, furnace proper. So loads are put into the vestibule, and then sequentially, they move their way through the furnace. So the first zone of the furnace would be what we would call the preheat. And that's where we're bringing the part up to temperature. And in this example where we're showing boost diffuse, so this is an example where we would be carburizing. And the first couple of positions would be a boost, and we carburize at a higher carbon content because it diffuses more rapidly at the initial point of carburizing. And then at the tail end of the carburizing cycle, we reduce the carbon content to what our desired surface carbon content would be. So an example might be, we would start out, we'd boost at 1% or 1% in change. And the diffuse cycle would be 0.8% carbon. You do that for a couple of reasons. You want to mitigate any retained austenite, so a higher carbon. With the bars quenched at a higher carbon, you have the opportunity for development of an unacceptable amount of retained austenite. At the extreme, you could start developing carbides, and those become very difficult to resolution. So that's the rationale for having a boost diffuse. You do that same thing in a batch furnace. I didn't describe that as such. And then the drop zone. So we want to reduce the temperature prior to quenching. And again, this is if we're talking about carburizing, we want to reduce the temperature prior to quenching so that we have very uniform quenching properties. And if the components that we're heat treating are distortion critical, it's very important as to what the temperature prior to quenching. So we carburize at a high temperature, 1700 Fahrenheit, 1750 Fahrenheit, because the diffusion rate is much higher at that temperature. But we only want to quench these parts at 1500 or 1550 because we want to have an absolute minimum amount of distortion. So every hour, the vestibule to the quench is going to open, and you would cross push that load into the quench vestibule. You would close the door, and then just as the animation described in the batch furnace, that load would drop on an elevator exactly into the quench. So now that we've done that, we have an opening. That last position is open. So we go to the vestibule on the front end of the furnace. We open that door, we put a load in there, we close the door, and we only close it long enough for us to reestablish the furnace pressure. Once we have, 3 to 5 minutes, no more than that. Once we've established furnace pressure, we can open the door between the vestibule and the preheat zone, the first preheat zone, exactly. And then to the left of the vestibule is going to be a mechanism for pushing these loads, hence the term pusher. So could it be hydraulic? It could. Could it be mechanical? Both are employed. And what you're doing is you're pushing it one position. Because the last position is open, the second to the last load progresses into the last position. The load that you put in the vestibule goes into the first position.
So
So the-
Michael, just a couple quick questions here. Just so the sequence starts with the load being pushed out of the furnace into the quench vestibule and then dropped in. That leaves that last spot open in the furnace. Then everything else starts and we push it all down. So we're pushing all of everything down, correct?
You are correct.
Yeah. I've got another quick question just for those who, and I'm assuming I'm correct on this, but I could be wrong. In this illustration, it looks like there are actually divisions between each of these different locations, if you will. In the preheat, it looks like there's 3 or 4. In the boost diffuse, looks like you've got 2 or 3, and then drop. Those aren't actually physical barriers. You're just showing where the load would progress to, correct?
You are correct.
Okay. Is there any chambers, quote unquote, any divisions in a pusher furnace at all?
So in a pusher furnace, you have arches above the load. And that helps to compartmentalize. The key word there is helps. You don't have a actual compartmentalization. So the preheating, let's just say that we want to perform a carburize at 1700 degrees in this furnace. The preheating, if you had 3 preheats, you may want to perform that something below the 1700. With the last position being at 1700, so that the load that goes into the carburizing zone is at temperature and it's ready to accept carbon. In the carburizing zone would be all at the same temperature, but you have to understand these parts are all at 1700 degrees. And we want to quench it at 1550, let's say. So we have two positions that we are going to allow the load to cool down to 1550 degrees. So would you want a zone arch there? I think that you would, yes. Would you want a fan in those zones? So if you had a fan in those zones and you are circulating the atmosphere through those loads, you have a better opportunity to attain a uniform temperature from the top to the bottom of the load than if you did not. So here's a pusher furnace system. And typically, not always, but typically pushers are put into a system because you have multiple operations that you have to perform. This is in a U. Okay, the loading and unloading are next to each other. This could be a linear layout. And in another life, I worked for a company in Syracuse, New York that had 14 furnaces that were all linearly oriented. So the person on the front of the furnace did one thing, the person on the back of the furnace did another, and they really didn't communicate. I personally am not a fan of that. I like this operation because you could have maybe 1 or 2 people performing the loading and unloading operation, and you could have a furnace operator who would be responsible for the overall control of this piece of equipment. But you can see we have 4 loads here that are however it was that we chose to fixture them, baskets, fixtures, whatever it might be. We've put a couple of parts in a preheat so we could perform that same cleaning that we talked about in preheating the load with low-cost BTUs. The preheat then goes into the vestibule. The loads progress down through the furnace as we had described. You get to the end and that load is quenched. It comes out of the quench. And just as we spoke about in the batch furnace, after it comes out of the quench, it's going to be 150 to 200 degrees plus. We want that to cool down to room temperature because the next operation is going to be washing. So we allow that to cool down to room temperature and then we put it in the wash. And we would wash it. Following the wash operation, right on the back of that wash, you might have a drip station. So whatever it was that you have washed off in the water, you don't want that to go into the temper. So following the drip station, then you would go into the tempering furnace. Here we're showing 3 positions, could be 3, could be 6, could be 9. This is just an example. Following the tempering operation, Then we would go out in that first position. You might have a blower underneath, and you would be putting circulating room temperature air through it up into a ductwork ahead. And that's how you would cool the room down to low temperature. Those loads would progress down that unload station. So at the very end, you're actually unloading the parts, perhaps for a subsequent shop blast cleaning operation or development of a rust preventative, or maybe they're just put back into the customer's container. In a captive operation, they might go into a container where the parts would go on to a subsequent grinding or hard turning operation. So here you can see that the loads progress into the preheat, they progress through the furnace, they go into the quench, they're put into the wash. It's pretty quick.
Yeah. It doesn't happen this fast in real life, everyone.
No.
Yeah.
So in the temper, it exits the temper and goes into the unloading station. So the point of this is to show that it progresses through the furnace. So as we'll speak about, the advantage is that you have very small loads. You have relatively small loads, not very, relatively small loads that you're processing. They very consistent process in the pusher furnace. And but what you're on for is that however you've designed this system, every load goes through every station. So you don't have an opportunity to easily extract a load as quenched and not wash it. It can be done. You could have a furnace designed to do that. It's not easy. After it's washed, as you can see in this animation, typically it's going to progress into the temper. Could you design a station that would allow you to offload it? You could. Normally, that's not how that's done. So it progresses through the temper, and then you go into where it is then subsequently unloaded. So as we'll talk about, if the batch furnace, if its strong suit was the fact that it's extremely flexible, particularly in a systemic kind of thing, the pusher furnace, as we'll learn shortly, its strength is productivity.
Yeah. Higher levels of productivity, but you've got to have the same, pretty much the same, if not the same product, at least the same process on whatever it is you're putting in there.
Bingo. So that's exactly what you have to have there. Yes.
Tune in for part 2 of this conversation to hear throughput and more capabilities when it comes to batch IQ versus continuous pusher systems. Follow and like the Heat Treat Radio podcast wherever you're watching or listening so you don't miss alerts when the next episode drops. If you'd like to get in contact with Michael, email mmoiseau@erie.com. That's M for Michael, Moiseau, MOUILLESEAUX @erie.com, or reach out to me and I can put you in touch. My email is bethany@heattreattoday.com. You can also connect with me if you have a new or interesting idea that you want to hear discussed on Heat Treat Radio, or would like to sponsor an episode. Heat Treat Radio would like to thank Heat Treat Veterans for sponsoring this episode. Share your service history at www.heattreattoday.com/veterans-nomination-page. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. And I'm Bethany Leone. Thank you for listening.